Alright, section 6.4 is on radioactive decay, and this is for me when the course gets, or the unit gets a little bit more interesting. It is getting more into the mathematical side of nuclear physics, and this is going to be a basis for a lot of the things that we're going to do a little bit later, although later we're going to get even more mathematical, Riley. So, transmutation describes a process by which an unstable atom of a given element changes into another element. So, we kind of talked about how the number of protons inside of an atom defines the element. Carbon always has 6 protons. If you have something with 6 protons, it is carbon. That is the definition of carbon. Now, if carbon undergoes transmutation, and for some reason, let's just say something comes in and plucks a proton out, you don't have carbon anymore. You have something else. So what we're dealing with here is a process where the element itself changes into another element. And if you take chemistry, especially in the grade up to grade 12, like you deal with a lot of chemical reactions, but you don't really deal with any nuclear reactions. Nuclear reactions is when a new element gets formed. So anyway, transmutation, that's what transmutation is. So we are dealing with a change in the number of protons, and we're dealing with unstable atoms. Okay, so for the most part, carbon is fairly stable. So we're not really dealing with carbon, we're dealing with our polonium and our plutonium and our radium and all those things that are very unstable. Now this new element may or may not be stable. Sometimes an unstable element will transmutate into a stable element and then it's done. Sometimes it will transmutate into another unstable element, which will transmutate into another unstable element, which will transmutate and transmutate and transmutate until it gets to a stable form. The series of nuclear transmutations occurs until that stability is reached, and the series of steps in the transmutation is called a disintegration series or a decay series. So we are dealing with something like decay is when you get radioactive decay happening. So that's what the topic of today will be. There are 3 types of decay that we're going to deal with. The first is called alpha decay. And alpha decay is when an alpha particle, also known as a helium nucleus, so a helium nucleus is an alpha particle, don't forget, is released from an element or from an atom, and that then creates a different element. So the general form for alpha decay looks something like this. Element X with atomic mass A and atomic number Z shoots off a helium nucleus or an alpha particle, and because of conservation of mass, the top numbers always have to add up. So for example, if 4 things in the nucleus are taken out, then our atomic mass of our element has decreased by 4, and if 2 specifically protons are released, then our Z number or our atomic number has decreased by 2. So the number of protons has decreased by 2, and therefore we have a new element, which is why we have this symbol Y instead of X on the other side. Now one thing that I can tell you is that this is called apparent it can be called apparent nucleus or apparent atom, okay, or apparent isotope, but the main idea here is that we're dealing with apparent. And usually we're talking about the nucleus because we're changing protons. This is called a daughter. Okay, and then because we have helium here, this is an alpha particle. No, they're actually called parent and daughter. I'm actually telling you that because the textbook will talk about a parent nucleus, and it's not specifically stated in the notes, and I'm not just making this up. Now, in this process, atomic number and atomic mass are conserved. So, like I said, the top numbers always have to add up. The bottom numbers always have to add up. to the left. So the top numbers on the right have to add up to the top number on the left. Bottom numbers on the right have to add up to the top bottom numbers on the left. So it's just like in chemistry when you're trying to make sure that there's the same hydrogens on the left that there are on the right. However, what you will find is that the mass of X is greater than the combined masses of Y and helium. So for example, if you were to physically measure the mass of this plus this, you would find that it does not add up completely to the mass of X. And we say that there's this missing mass. And this missing mass is actually converted into kinetic energy for this alpha particle. So this alpha particle is actually going to get shot out of that parent nucleus. And in order for it to get released or shot off, that means that it has to have some kind of speed. That speed must come from somewhere. So it comes from this decay process. And what we'll find, and this is kind of interesting actually, Einstein's equation E equals mc squared, what he says there is that energy is mass, and mass is energy. So what happened was some of this mass was converted into energy from Einstein's equation, and that energy was able to shoot this helium particle out. Now, we're not going to deal with that right yet, but we will get into Einstein's E equals mc squared equation in a little while. So, how do we use this information? Well, a lot of times you'll be asked to write decay equations. So, we want to write the alpha decay equation for uranium-238. So, this is our parent nucleus. This is the thing that we're starting off with, and we're going to alpha decay it. So, what would happen? So you're going to start off by writing the symbol of your elements. So in this case it's uranium, so you'd write a capital U. Riley, what's that? It defines our isotope, but what specifically number? What numbers? It's our atomic mass. That is our top number. Okay, so that's going to go up there. BG, could you guys let me know what the atomic number is for uranium, please? So you can find that on the periodic table. Thank you. Now that's one thing that isn't outright stated in our isotope. Like it says uranium-238. However, since it tells us that it's uranium, that means that the atomic number must be 92. Now because we're dealing with some kind of equation, like some kind of reaction, in this case it's a nuclear reaction, it's nuclear decay, we do need an arrow here. So we are kind of in the realm of chemistry in some respect. Now what we're saying here is that the alpha decay is happening. So if alpha decay is happening, I'm going to start off by saying that my helium is going to be getting shot out of here, and alpha particles always look like this. Helium, 4, 2, 4 for the atomic mass, 2 for the atomic number. No, yes, if we're not dealing with alpha decay, we will have another particle, so either a beta particle or else a gamma particle. But here it specifically tells us that it's alpha decay. That's a good question, but it is specifically telling us that it is an alpha particle. Okay? Now what we want to do is figure out what our other element is. What element has uranium become? So the first thing that you want to do is say, well, I started off with 92 protons, and 2 of those protons have now left. So Brandon, can you help me out here? What is my element on the periodic table that has 2 protons less than uranium? Okay, thorium, which I think is TH, and 2 protons less than 92 would be 90. Now we also know that the atomic mass has, well, we started off with 238 particles within our nucleus, and we're losing 4 of them. So we just subtract that. 238 minus 4 is going to be 234. Now when I say that the top number and the bottom number need to be conserved, 234 plus 4 is 238, so that works out. Because we lost four things in the nucleus. No, you never, when you're dealing with isotopes, you never worry about the atomic mass on the periodic table when you're dealing with isotopes. So what is it on the periodic table? Okay, on the periodic table, if you looked up thorium, it would have an atomic mass of 232. That is not the case. That is the average. Here we're talking about specifics. Any questions there? So as long as you're making sure that the top number and the bottom number are adding up, then that's good. All right, beta particles. Yep. Beta decay. So if alpha decay is when an alpha particle is shot out, then beta decay is when a beta particle gets shot out of the nucleus. When a beta particle gets shot out, what's actually happening is we're shooting out an electron. But it's released from the nucleus. And we all know that electrons don't belong in the nucleus. So what has happened? A neutron actually can break up into a proton and an electron in beta decay. So one thing that I said to you before was that neutrons are this very, very slightly heavier than protons. And that's partly because a neutron can break up into a proton and an electron. So that missing mass then between the proton and the neutron is probably the mass of an electron. Now, what happens after the neutron breaks up into a proton and an electron is the proton stays within the nucleus and we get an element change. So the element then changes because the number of protons is changed and the electron is shot out. Since the electron has negligible mass, the atomic mass itself does not get changed. So it has a general form of element X turns into element Y plus a beta particle. Now remember that a beta particle is just an electron. Here is the, symbol for an electron or beta particle. Now right here, notice that the atomic mass for your new element or your new isotope will not change. So whatever it was before, it's going to be after. And note that A plus 0 is still equal to A. So that conservation is still there. In alpha decay, the Z decreased by 2. And in this case, the Z is actually going to increase by 1 because, like I said, that neutron is turning into a proton, increasing the number of protons in the nucleus. And Z plus 1 minus 1 is equal to Z. So just for the record here, you might want to put on here that this is a beta particle or an electron. Nope, Z increases by 1. No, I'm saying when you go to make sure that your bottom numbers add up, so on the bottom, if you go Z plus 1 minus 1, you're going to get Z. Right? So that conservation is still there. If you go A plus 0, you're going to get A. And that's still there. So that's where the conservation comes into play. All right. So again, I kind of said this last time, but the mass of X is greater than the mass of Y. So your mass of your original parent is greater than the mass of your electron and your daughter nucleus combined. And the reason why is because some of this mass inside the nucleus has been converted to energy to expel that electron outwards. So what I'm going to do is I'm going to give you guys a second to try to do the beta decay by yourself for sodium-24. Okay, so I want you to take a second and write down what you think the beta decay looks like. All right, so hopefully you had a chance to try this out for yourself. Again, this number right here is the atomic mass, so it's telling us that we're dealing with sodium. 24 is the top number, and sodium can only exist with a certain number of protons within its nucleus, which is 11. So it's going to start off with sodium, 24 is atomic mass, 11 is the atomic number, and then we are going to beta decay. So I usually start off, I like to write my decay second. It doesn't matter if you put that first or second, but I like to put it second. And then I like to do that first because I like to remind myself what I'm doing. Oh, I'm doing beta decay. Okay. Now, what I want to do is recognize that my daughter nucleus is going to be whatever my atomic number was before, plus 1. So 11 plus 1 is 12. And my atomic mass stays the same. So if it was 24 before, it's going to be 24 afterwards. And the element that has 12 protons in its nucleus is magnesium. So I have changed the element by changing the number of protons in the nucleus. Alright, the last type of decay is some of the easiest, but some of like kind of the weirdest to explain. So gamma decay is the last type, and it is the release of excess stored energy within the nucleus. Now this type of decay does not cause transmutation. We are not changing the element here. All we're doing is getting rid of excess energy. So therefore we're not getting a new element here, but we're going to show the decay still. Now although a new element is not formed, gamma decay is a regular staple in a decay series. A decay series will usually show the gamma decay, but you will see that there's no change in the actual element after gamma decay. Now this process occurs when a nucleus is excited by the bombardment of photons, which is just light and energy, and returns to a non-excited state. So a lot of times a nucleus will get hit by energy like light, X-ray. Well, X-rays are pretty intense, but maybe ultraviolet rays or something like that, high energy light that will excite the nucleus, and the nucleus doesn't really know what to do with that extra energy. So what eventually happens is it just throws it outwards as gamma radiation. Now this settling down of the nucleus requires it to get rid of this extra energy, and therefore the nucleus expels a gamma ray. So what we usually show, or the way that we usually show this, is we usually show this with a parent nucleus with a little asterisk above it. That little asterisk means it's excited. It has some extra energy. These are unstable. These are unstable, yes, because there is this extra energy here, and it needs to do something to get rid of it. So what it does is it expels this gamma radiation, which is dangerous, right? Now note that in the end, what we get is our daughter nucleus. Taryn, please. What we get is this daughter nucleus. It still is X though. So the actual element itself does not change. However, there is no asterisk on it anymore, so it's no longer excited. But in the process, this gamma ray has been expelled. So this is some of the easiest ones to do because nothing changes. You just add a gamma ray. So for example, write the gamma decay nuclear equation for uranium-238 in an excited state. So what it's telling us right away is that we're dealing with uranium-238 and it's excited. So uranium-238 with an atomic number of 92, and it is excited. Yeah, the asterisk means excited. That is going to release a gamma ray, and it has no atomic mass and no atomic number. It is strictly energy. That's all it is. It is high energy light waves. If the question for some reason doesn't say excited, still make it excited, because it can't release that gamma radiation except for in an excited state. Okay. Now we still have uranium-238 with atomic number of 92, but now it's not excited anymore. It has gotten rid of. It has settled down. It took a nap. Yeah. Now, one thing that I'm going to say to you, and this will come up in probably this set of questions and later sets of questions and quizzes and all sorts of places, but a neutron will often be depicted as this. an atomic mass of 1, but an atomic number of 0, and then just a little n. Sometimes it will be in the decay series that you see. It'll be in the nuclear equation that you see. Sometimes there'll be a neutron expelled, and this will become more common when we get to like nuclear fusion, for example, nuclear fission. Depends on the question. So when you see a need for it in these questions, you will use it. When you see it, you will recognize it, and you might not, but it will definitely come up later. Yeah. So here are the questions that we're going to do. So if you can write those down, please. We will be doing a quiz for this section. I'm just going to check to see if it's going to be tomorrow or the next day.